Welcome to clickmyproject.com. Let's discuss about the product. Our product is 1.2 volt 10-bit 75 ms pipelined ADC with phase dependent gain transient CDS. A phase dependent gain transient corrected double sampling technique is proposed and applied to a 10-bit 75 millisecond pipelined analog to digital converter, that is hereafter mentioned as ADC converter. This reduces the accumulation of prediction error of each multiplying operational amplifiers without the need of additional capacitors and switches at the output. With a 10 MHz sinusoidal input, a prototype fabricated in a 0.13 micrometer CMOS process has a 56 dB signal to noise plus distortion ratio, that is SNDR ratio, and a 64.57 dB spurious free dynamic range. Analog to digital converters are essential interface between the analog and digital systems. There are number of different ADC architectures designed for different mixed signal VLSI systems. Among these architectures, a pipelined ADC can achieve a good balance between accuracy and conversion rate with low complexity and low power consumption. However, as the scale of CMOS process continues to shrink, it has become difficult to improve or even maintain the accuracy of the pipelined ADC because it relies on high gain operational amplifier, that is op-amp, and well-matched components. An immediate problem is that the combination of deep submicrometron process and low power voltage makes it difficult to realize an op-amp with a high open loop gain without sacrificing bandwidth. A promising method of compensation of op-amp which for gain error is the corrected double sampling, that is CDS technique. This can increase accuracy without additional circuit complexity and power consumption. That means for this design we doesn't require any extra power, so we can optimize the power consumption, and also it's not a complexity design. We propose a novel phase dependent gain transient CDS technique, which is another efficient way to reduce prediction errors without using additional capacitors. By utilizing a very low gain op-amp, we reduce the prediction error by providing a slightly higher DC gain during the pre-amplifier phase, although this is still much lower than the gain of conventional op-amps commonly used in pipelined ADCs. To provide high gain, we apply the partially switched op-amp techniques, in which auxiliary regulating amplifiers are turned on and are simply attached to the low gain op-amps of the amplifying phase to form the folder cascade with the regulated gain boosted amplifiers. In this way, we reduce design effort and minimizing the additional power consumption. Let's see the black diagram. So this is the flow of our process. So as we already discussed, our design is based on CMOS design methodology. So for this design, we have to use Tanner EDA as an implementation tool. So among overall this design, we have to include some similar blacks. So initially we have to process sample and hold and CDS blacks, and also we have to adapt comparator design inside this. And for overall design gives us a ADC circuit, and we have to get ADC out by simulating in WEdit. So in the WaveEdit, by the simulated results, we can analyze the performance result, and our performance results will give better performance than the previous methodologies. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool, that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions, that is called SEdit, LEdit, WEdit, and such more. There are lot of under devices. So in this we are using SEdit for circuit designing, So, and then after we design that edit, while simulating, the circuit's design will pass through the T-space that we can understand through the checklist generated through the SPICE code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-space. So, we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is a cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to set up simulation. In the setup simulation you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-space. So through T-space you can see what are the checklist available in T-space. In T-space usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-space codes are called netlist. You can run either from SEdit or from T-edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.